Hello and welcome back for lecture 4. Today we'll be continuing in page 15 of the handout. We'll be talking about cliques, independent sets, and graph complements. Okay, so in today's lecture, we'll focus only on simple graphs. These are graphs without loops. So a loop is an edge that has the same starting and ending vertex. So we won't have any of these. And we won't have any double edges. So if we have two vertices, we won't have two separate edges between them. There can only be one edge between every pair of vertices. So let's start by looking at this problem. Suppose you browse through your Facebook friends list and you find the following information. So Alex is friends with Diego, Elena, and Fred. Brianna is friends with Charlie, Diego, and Fred, etc. We have all this information about who is friends with whom. And we want to invite the largest number of people possible to lunch so that each person in the group is friends with everyone else. So if we want to draw a graph that represents this data given here, how can we do that? So remember, our vertices are our objects, and the edges are the connections between them. So I would say the objects here are the friends, and the connections between them are that two objects are connected if those people are friends with each other on Facebook. So we can draw a graph. We'll have 6 vertices. We can label them with A, B, C, D, E, and F. Okay, and we'll draw an edge between two vertices if they're friends with each other on Facebook. So Alex is friends with Diego, Elena, and Fred. Brianna is friends with Charlie, Diego, and Fred. Charlie is friends with Brianna. Diego is friends with Alex, Brianna, and Elena. Elena is friends with Alex and Diego, and Fred is friends with Alex and Brianna. Okay, so this is our graph. Okay, and so we wanted to invite the largest number of people possible to lunch so that each person in the group is friends with everyone else. Okay, so if we let G be a graph, and we let S be the set V1 through Vn of vertices of our graph G, then we have the induced subgraph, which we write G bracket S. This is the subgraph of G containing only the vertices in S and the edges of G that have endpoints in S. So let's look at an example. Let's let S be the set of vertices A, B, and C on this graph here. So I want you to pause for a second and draw the induced subgraph G of S for this graph. Okay, now that you're back, what is the induced subgraph G of S? So what we want are the vertices in S, so we want A, B, and C, and we want the edges of this graph that only have endpoints only in S. So the endpoints are only the vertices A, B, and C. So that will be this part of the graph right here. And it looks like this. We can draw it to the side. So we have only the vertices A, B, and C, and only the edges that contain these vertices as endpoints. Okay, so a clique, or some people call it a clique, of a graph G is a set of the vertices of G such that every 2 vertices in this set are adjacent to each other. So let's get right to an example. Let's find a clique of size 3 in this graph here. So we want a set of 3 vertices such that every pair of vertices is adjacent. So what does that look like? Well, it looks like a triangle. And we can identify this triangle right here as a clique of size 3. Okay, if you take any pair of these vertices, there's an edge between them. So let me ask you this question. In order for a set of vertices S to be a clique, what must be true about the induced subgraph G of S? What I mean by that is which type of graph is it? Why don't you pause for a minute and try to think about that? Now that you're back, let's talk about it. So if the induced subgraph of this set of vertices is a clique, that means that each pair of vertices is adjacent. Okay, so if we draw, let's just say our induced subgraph has 4 vertices, then for every 2 vertices, there's an edge between them. So do we recognize this type of graph? This is the complete graph, okay, on whatever number of vertices we have. So which type of graph is it? It's a complete graph. Remember, that's the graph where each pair of vertices is adjacent. So each pair is connected by an edge. So now you can start to do this example on your own. What's the largest clique size in this graph here? So why don't you pause and figure that out? Okay, welcome back. So let's find the largest clique size in this graph. Well, right away I notice a triangle. We have this group of 3 vertices, they're all adjacent to each other. And is there anything bigger? Yeah, in fact, if you look at this part of the graph right here, okay, each pair of vertices is connected by an edge. And if you think about pulling this vertex out to the side here, you'll recognize it as K4, what we drew right up here. So we found a group of 4 vertices where every pair of vertices is connected by an edge. So the largest clique size here is 4. And I guess I should say, do we have a group of 5? Well, no. There are only 5 vertices in this graph, so if we added in this vertex isn't adjacent to all of the other vertices. So this idea is called the clique number, and we denote it by omega of G. So the clique number of a graph G is the size of the largest clique in G. So the clique number of this graph up here, omega of G, is 4. So let's say we have a graph G, and it has 7 vertices labeled V1, V2 through V7. And the degrees of the vertices are listed here. So is it possible that the clique number, omega of G, is 5? Why don't you pause and think about that? Okay, welcome back. So is it possible for the clique number to be 5? So how does the clique number relate to the degrees of the vertices? Well, if our clique number is 5, that means we have an induced subgraph that is K5, the complete graph on 5 vertices. And what are the degrees of all of those vertices? Well, each vertex is adjacent to all of the others. It's adjacent to 4 others. So the degree of that vertex in the induced subgraph is 4. That means that the degree of 5 of the vertices in our original graph G has to be at least 4. Okay, so let's look at the vertices that have degree at least 4. We have V1, V2, V3, and V5. Okay, but there are only 4 of these vertices. We need 5 of them to have K5 as an induced subgraph. So no, it's not possible for the clique number to be 5. So no, it is not possible because there would have to be at least 5 vertices of degree at least 4. So now let me ask you this. How can you tell how many 2 cliques there are in a graph? So pause and think about that. Okay, so how many 2 cliques are there in a graph? Well, what is a two-clique? We have a set of two vertices, and every pair, there's only one pair, is adjacent. So there's an edge between these two vertices. Okay, so the number of two cliques is just the same as the number of edges. Okay, so a two-clique is a pair of vertices that are connected by an edge. Therefore, the number of two cliques is the same as the number of edges. All right, so now what is the clique number of a cycle? And note there's not necessarily one answer for all cycles. So why don't you pause and think about that now? Okay, welcome back. So what's the clique number for a cycle? Okay, remember a cycle is a closed path. So we can start with a cycle of length 3. That will be a triangle. Okay. So what's the clique number here? It's the maximum number of vertices where every pair is adjacent. Okay, so if we take all 3, they're all adjacent to each other. Okay, so the clique number of this graph, if we call it G, is 3. Okay, but that might not be true for all cycles. So moving up in length, we can have a cycle of length 4. Okay, and what's the clique number of this square here? Well, we don't have any triangles. Okay, so the maximum number it can be is 2, and we do have edges, so we do have 4 separate two cliques. But again, no triangles, so the maximum clique number is 2. We can extend this to a cycle of length 5. Okay, again, there are no triangles here, and in fact, for any cycle with length greater than or equal to 4, we won't have any triangles. Okay, so the answer is the clique number is 3 for a cycle of length 3, and the clique number is 2 for a cycle of any longer length. So now let's solve our problem from the beginning of the lecture. Okay, remember we wanted the largest number of people possible so that each person in the group is friends with everyone else. Okay, so we're looking for the clique number of this graph. And let's determine what that is. So why don't you pause and figure that out? Okay, so now that you're back, we don't have a group of vertices whose induced subgraph is K4, the complete graph on 4 vertices, but we do have a triangle here. Okay, that's a clique of size 3. So our clique number is 3. Okay, so I'll move on to a similar idea, something called an independent set. So now let's suppose that we're given the same group of friends and relations as we had before, but now we want to invite as many friends as we can who don't know each other, so that everyone can make new friends. Okay, so what we're looking for here is called an independent set. So an independent set of a graph G is a set of vertices of G such that no 2 vertices are adjacent. So it's kind of the opposite of a clique here. And the independence number, denoted alpha of G, is the size of the largest possible independent set of G. Okay, so what's the independence number, alpha of Kn, for any n, where Kn is the complete graph on n vertices. Okay, so we're looking for the size of the largest possible independent set, so the size of the largest possible set of vertices such that no two are adjacent. Well, what does the complete graph have to do with adjacency? Each pair of vertices is adjacent, so if you're going to take any set of two vertices, they're going to be adjacent to each other, so they don't form an independent set. For that same reason, you can't take any bigger set of vertices. But if you just take one vertex, it's not adjacent to itself, so that single vertex forms an independent set. So, whoops, it's not omega, it's alpha, the independence number of Kn is 1. So let's think about how this idea relates to colorings of a graph. So how can we obtain independent sets of a graph if we're given a coloring of the graph? So think about what colorings have to do with adjacency. So pause and think about that for a minute. Okay, welcome back. So let's think about what a coloring of the graph is. So remember that a coloring of the graph is a coloring of the vertices, or an assignment of colors to the vertices such that no two adjacent vertices are the same color. So what happens if you pick one of the colors that you chose for your vertices and you look at all of the vertices that are that color? Will any of them be adjacent to each other? Well, the answer is no by the definition of a coloring, right? No two vertices that are adjacent can be the same color. So if you take all vertices of one color, none of them will be adjacent to another. Okay, so this forms an independent set. Let's practice finding the independence number alpha of G for these two graphs. So you should pause and do that first. Now that you're back, let's talk about how to find the independence number. So we want the largest set of vertices such that no two vertices are adjacent to each other. So looking at this first graph, what if we chose this middle vertex here? Could we include any of these other vertices? The answer is no, because they're all adjacent to this vertex. So that tells us, that we probably don't want to include that middle vertex. So what if we include one of these outer vertices? Then we want to try to find other vertices that are not adjacent to it. Okay, so we can't pick any of these. So we move on to this one. Then we can't pick any of these, but we can pick this one here. So we've found 3. And since this graph has symmetries, this is the biggest independent set. And it has 3 vertices in it, so our independence number is 3. Okay, now looking at this graph, again, if we choose this middle vertex, we can't put any other vertices in the set because they're all adjacent to this one. But if we pick one of these outer vertices, then we can pick all of the other outer vertices because they're not adjacent to that first vertex. Okay, so that gives us 6 vertices in this independent set. So alpha of G is 6. Okay, and lastly, we'll tie these two ideas together with something called the complement of a graph. So the complement of a graph G, which we denote as G with a C in the superscript, is the graph with the same set of vertices as G, but there's an edge connecting two vertices in the complement if and only if there is no edge connecting those vertices in G. So we start with the graph G, we get rid of all the edges in G, and we add in all edges between every pair of vertices where there's no edge in the original graph. Okay, so in other words, another way of saying what I just said is we obtain GC, the complement, from G by filling in the remaining edges to get the complete graph. That's where each pair of vertices is connected by an edge, and then erasing the edges that we started with in G. So if we want to draw the complement of this graph here, you can try it on your own first if you want, and pause. But otherwise, I'll draw it for us. So there's an edge connecting two vertices if and only if there's no edge connecting them in this graph here. Okay, so what are the edges missing from the complete graph on 4 vertices? Well, we're missing this edge, and we're missing this edge. Okay, all the others are there. So in our graph complement, we just include those blue edges I drew in. And we don't include any of the edges that were in G. Okay, so this is the complement of G. So what's the complement of the complete graph, Kn? So pause and think about that for a minute. And let's talk about that now. So the complete graph has an edge between every pair of vertices. So if we're going to take the complement, we're going to fill it in to get the complete graph. We already have that. And then we're going to erase all of the edges we had in our graph to start with. So we're going to erase all of the edges of the complete graph. So the complement of the complete graph is the graph with n vertices and no edges. And similarly, what's the complement of a graph with no edges? Well, we can think of the same process. We can fill it in to get the complete graph, and then erase the edges of the graph we started with, this graph with no edges. So we're not erasing anything from the complete graph. So this will just be the complete graph on that number of vertices, however many we had to start with. Okay, so is it true that the complement of the complement graph is equal to G, our original graph? And why or why not? So pause the video and think about that. Okay, let's talk about it. So we're going to take the complement and then take the complement again. So let's think about the edges that are in G. Okay, to take the complement, we erase. So let's say first, if E is an edge in G, then to take the complement, we remove E. But then, to take the complement of the complement, that's this G to the C to the C, we put E back in, since it's not in G complement. Okay, so all the edges of G are in G complement complement. Okay, if an edge, just call it F, is not in G, then when we take the complement, we add it in. And then when we take the complement of the complement, we remove it. So yes, it is true. All of the edges that are in G complement complement, and all of the edges not in G are also not in G complement. So let's think about cliques and independent sets again. What happens to a clique G, a clique of G in G complement? So pause and think about that. So what happens to it? Well, a clique, remember, is a group of vertices where each pair is adjacent. So if we're taking the complement, we're going to remove all of those edges. So if in G all of those vertices are adjacent, then none of them are adjacent in the complement. Okay, and what is that called? That's called an independent set. So a clique becomes an independent set, right? Now none of those vertices are adjacent to each other. So what happens to an independent set of G and G complement? Well, it's the same idea. In G, no pair of vertices is adjacent in the independent set. So when we take the complement, we add in edges between each pair of vertices, and now they're all adjacent to each other. So we get a clique. So an independent set becomes a clique. Okay, so what does that tell us between the relationship, or about the relationship between omega of G, the clique number of the graph, and alpha of G complement, the independence number of the complement of the graph? Okay, so the clique number is the size of the largest clique. Okay, and the independence number of the complement is the size of the largest independent set in G complement. So the largest clique in G, by what we just talked about earlier, will become an independent set in the complement of G. Okay, and this independent set will be the largest independent set. So if we assume there's an independent set that's even larger, then if we took the complement of the complement, that would give us G, remember, like we said earlier. And in G, the independent set becomes a clique. So that would tell us that there's a clique that's bigger than the one we had before. Okay, so the values are the same. Okay, so that's it for this lecture, and I'll see you in the next one for the 5th lecture on an introduction to graph theory.